Now we are going to discuss about the existence of a Taylor series for a given function. Well, before that, let's have a look at the calculation that we did in the beginning of this section, right? So there what we did was, in order to find the Maclaurin series for the function ex, we just differentiated, like we just wrote down these terms and then we differentiated them step by step and substituted the center, which is 0 in this case, and obtained these coefficients. After that, we were able to figure out a certain pattern for any general coefficient an, and that says for any coefficient an, it says that it is equal to the nth derivative of the given function evaluated at the center divided by n factorial. So this gives the impression that for any function, if you are given with any function, and if you can find, now if we need to write down that function as a power series at the given point, then it gives the impression that the only thing we need is this relationship, right? So basically, if we can find the derivatives of f, then we can directly calculate Cn's. So in other words, this calculation will lead us to the impression that if the given function is differentiable, then we can write down the power series, right? So that's kind of the idea you will get from this sort of a calculation, right? So when I say differentiable, since we are taking the derivatives for all the orders, it's like we need to get the first derivative and the second derivative, third derivative, and likewise as we have to get all the derivatives, we think that it is necessary, like if this function is infinitely differentiable, that means if we can find all the derivatives of f, it's like the first derivative, second derivative, third derivative, likewise if we can find all the derivatives of f, then we get the impression that so we can write down this Cn's, hence we can write down the power series. So that's the normal impression that we get when we follow through this calculation, but unfortunately that impression is not correct. Okay, so I will tell you why. That's kind of strange, right? Yeah, I know. So now the reason is there can be functions where that function is infinitely differentiable, but the power series does not make any sense. So I'll tell you an example. Well, if we consider this function, now this is kind of a result that the mathematicians have found. It's like you are not expected to think about this example at once. Okay, so 1 over x squared, our function is this one. For x not equal to 0 and when x is equal to 0, you have 0. And if you plot this function, it will look like this. It's somewhat like this. Okay, and now just by looking at it, even you can see that it is differentiable throughout. See, at 0 even you have a differentiable point. Okay, so now we are trying to figure out whether this function has a Taylor series at 0, or in other words, we are going to see whether this function has a Taylor series, a Maclaurin series, right? Okay, so now about that differentiability, well, we can use the fundamental relationships of differentiability, and directly we can prove that this function fx is differentiable, right? It's differentiable. So for this, if you need to do a exact proof, we will have to go through the definitions of differentiability. There, through a certain limit, we can directly prove that it is differentiable. Okay, so this is proved. And so now, and also not only once, but we can prove that the function fx is infinitely differentiable, right? So we can prove this one as well. Now for this proof, it's not very obvious, right? So it's like you have to do some calculations, and anyway we can come to this conclusion through the basic definitions of differentiability, right? And then, so now we have a function which is infinitely differentiable, and so in that way, that means, so we can get any derivative of f. So if we relate those derivatives with this equation, and if we try to try to obtain a power series, then we will be in a certain trouble. That is, now, although it is differentiable, right? If we go through those basic definitions of the derivatives, we can find that the derivative of f is also some kind of a piecewise function. Okay, so if we use the chain rule and everything correctly, we can prove that, we can show that the derivative of f is like this, right? So now it says that at 0, right? Now these equations you cannot, like, it's not very direct. Okay, it's like you have to do some calculations and apply the chain rule properly, and that's how you have to obtain these piecewise functions. Okay, say if we have successfully done this one, right? So now we have that the derivative of fx is like this. At the points which are not equal to 0, the derivative behaves like this, and at 0 the derivative will be like this. So for example, let's say the derivative of the function at x equals 2 will be the thing that you obtain when you substitute 2 in here, right? So, and the derivative of function at x equals 0 will be equal to 0. Okay, so that's the way you obtain the values from these piecewise functions. Okay, so, and also we can show that for all the derivatives, for any order derivative at 0, it will still maintain this piecewise property, and at 0 you will get 0, right? So any derivative evaluated at 0 will give 0 out. Okay, So now so far what we have done is we have a function which is differentiable, and we can prove that it is differentiable, and not only that, we can prove that it is infinitely differentiable. And then when we find the derivative, now I didn't do all these proofs inside, okay, like the inside calculations were not done in here. I just want to get the results only, okay, because doing those calculations is not the main point of this explanation, right? Okay, so now we have a function which is infinitely differentiable, and if we find the derivative of fx, it will look like this, right? And for all the other higher order derivatives, that means the first derivative, this is the first derivative, and the second derivative, third derivative, and likewise for any derivative evaluated at 0 will give 0 as the output, okay, right? So having that in mind, how about the coefficients of our power series? Now if we have a power series for this particular function, right, if we have a power series centered at 0, so here the x minus a part will vanish, so you will have only xn terms, right? Then Cn will hold this relationship, right? That means now we have already proved that, like we can prove that for any order derivative, for any nth derivative evaluated at 0 will give 0 as the output. So that means this one will be 0 no matter what n we choose. That means all the coefficients of the power series will be equal to 0. In other words, if this function has a power series, then it will be equal to 0. So in other words, what it says is the function is equal to the 0 function. So no matter what x we use here, you should get 0 as the output. But clearly it is not true, because if we use an x value which is not equal to 0, say for example 10, then to evaluate the value of our function at 10, we use this relationship. So 10 goes to this set which is not equal to 0, and the value of the function will be e minus 1 e to the power negative 1 10 squared, which is clearly not 0, right? But if it has a power series, then even at x equals 10, which is a non-zero value, you should get 0 as the answer. So if it has a power series, what you should get is 0, right? So it's like we have the same function. In one case you have f10 as e to the power negative 1 over 10 squared, and this case you have 0. So these two should be equal if this power series holds true, but clearly these are not equal. So the only possible mistake that we can have is to assume that we have a power series for this function. So that's the problem we have, right? So now, although this function is infinitely differentiable, this function cannot have a power series, because if it had a power series, then that will lead to these sort of contradictory results. So the only conclusion that we can take from this one is, all this calculation is, fx does not have a Maclaurin series, although it is infinitely differentiable, right? So Now the main point that we can get from that calculation is infinite differentiability of a function does not guarantee that it has a power series, right? So infinite differentiability does not imply that the function fx has a power series. This does not imply that the function has a power series. This is a arrow stands for the implication, and this cancellation means it does not imply that the function has a power series. So now we need a new condition to prove the existence of the power series. So just because you have a function, it does not say that it has a power series. Okay, so we need a certain condition to satisfy in order to be confident about having a power series for the function. It's like if we have a certain function and if it satisfies this condition, then we can safely say that the function has a power series. So what should this condition be? Now clearly we saw that this condition is not the infinite differentiability. There should be something more. Okay, but anyway, if it is not differentiable, then clearly it does not have a power series, right? Because if it has a power series, then definitely this relationship should hold true, right? So if it can't be differentiated, then we can at once say that it does not have a power series. But the thing is, the differentiability does not guarantee the existence of a power series, right? There should be something greater, like something more than this for the existence of the power series. So now in the next video I will explain the required condition for the existence of a power series.